Hello, in this video we're going to talk about activation energy and the Arrhenius equation. Okay, so up until now we've talked about kinetics, how fast does the reaction go, mechanisms, how does the reaction go about doing what it does, and now we want to think about, okay, for a given mechanism, what could make it go faster or slower, and how is that defined? So reactions occur when the molecules collide. For bonds to break, new bonds to form, etc., they have to run into each other. So how often does this happen? Very, very often. You have some sample of gas at atmospheric pressure, there's a ridiculous number of collisions happening every second. Well, obviously, since all reactions aren't immediate, that not every collision results in a reaction. Sometimes they just bounce off each other. It takes molecules with a certain amount of energy to be able to collide and react. So, alright, roughly the rate of reaction depends on these things. This is kind of a very big picture schematic definition of it, but it's good enough for our purposes. So, the rate of reaction depends on collision frequency, how often these molecules run into each other, and as you increase the concentration and increase the temperature, this will happen more frequently. Then the thing in the middle here, the fraction of collisions that have this required energy, that's known as the activation energy. The energy required when two molecules collide in order to proceed through the reaction. Then the last bit here depends on the shapes of molecules. If you're reacting on the left side of the molecule and your other reactant hits the right side of the molecule, nothing's going to happen. Okay, so going back to this equation here, let's put some variables on this. So we'll call the collision frequency Z, we'll call the fraction of collisions with the right orientation P, then in the middle, this fraction of collisions with the right amount of energy is related to this. E to the negative activation energy, this EA, divided by the gas law constant and temperature in Kelvin. And that set of terms relates to this fraction of collisions with the right energy. So we can put this all together. The reaction rate constant is equal to these things multiplied by each other. And then we usually just group P and Z together because there's not an experimental way to tell them apart. And so we just group them together into one constant. And we generally assume that this constant doesn't vary with temperature, which is actually not a great assumption, but it's one that we tend to make a lot, especially in the Gen Chem context. So we kind of assume that A is constant with temperature. So this is called the Arrhenius equation, named after the chemist who first postulated these ideas. And okay, EA is the activation energy, and so this is a constant for a particular reaction. Different reactions have different activation energies, and the units here are, say, kilojoules per mole. And then A, it's called the frequency factor, or I've heard it called the pre-exponential factor. It's a constant, and the units there need to match the units of the rate constant, K. So, alright, what is activation energy? So, molecules react when they collide, and you need some energy in order to make this happen. Why? Because during a collision, this kinetic energy is converted into vibrational energy and other things in the molecule that makes the reaction happen. And you need enough of this energy in order to break the bonds and make the reaction go. It's just like, common sense. If you have two things, if you smash them together harder, you're going to make more of a reaction. Okay, so this kind of sums it up. You break this bond, you need enough energy. EA is the activation energy, and only a fraction of collisions have this. And then just another vocab thing. Reactants that have this activation energy are said to be activated. Okay, we'll see that word come back. And now looking at temperature here, okay, this is a blast from the first semester of chemistry, a blast from the past, I should say, and it's the Maxwell-Boltzmann distribution, and it tells you, at least in the gas phase, how the kinetic energy of molecules varies with temperature. And what we see is, okay, this little plot on the right, the x-axis is kinetic energy, the y-axis is how many molecules have that particular energy, and this distribution of molecules is both narrower and lower energy on average if you have a lower temperature, T1 say, and if you increase the temperature, for example T2, you get a broader distribution and then more molecules are of higher kinetic energies. So then if we have this activation energy, only molecules over here in this camp are going to have enough energy to actually react. And so at a lower temperature, it's a smaller number of molecules. And at a higher temperature, there's more of them. Okay, another thing we need to talk about are reaction coordinates. And so these are abstract, one-dimensional plots that show how it is going from the reactants to the products. And so I'll put the plot up here. And remember, the x-axis here is much different than the last plot you looked at, the Maxwell-Boltzmann distribution. And so the x-axis just shows you progress. It's not to scale, that doesn't matter at all. It's just saying on the left is where you start, and then you work your way towards the right. But the y-axis does matter. The y-axis here is energy. So let's use the example of hydrogen gas and oxygen gas coming together to make water vapor. So you have reactants on the left in this spot over here. And then in the middle, you have what's called the transition state, or the activated complex. And so this transition state, sometimes if you had like a simple reaction that occurred by one elementary step, you could imagine this as just the intermediate, I don't know, all these molecules jammed together before they then come apart as the products, something like that. Sometimes when you get into bigger organic molecules, you can start to define what this looks like. But it's basically the highest energy state along this path. And the difference between the reactants and this transition state is the activation energy. You need to absorb that much energy in order to get up to this transition state. And then once you do, then it's easy sailing to get to the products. And so the difference between where you started and where you ended up is the overall energy change for this reaction. And so this shows us an exothermic reaction. The products are lower energy than the reactants, and so delta E will be negative. Whereas you could show this for an endothermic reaction, and okay, your products are higher energy than your reactants, and your delta E is positive. But overall, the rest of this is pretty much the same. Another thing I want to point out is this little dagger, the AB with this kind of double dagger on it. And that is one way that we represent transition states. Sure, AB here is kind of generic, but we can write a chemical formula with this double dagger after it, and that will show that it's the transition state. And then I like this plot, so I'll show it. This is another way to conceive of these ideas. So on the right is what we just looked at, the reaction coordinate over here. And on the left, we have the Maxwell-Boltzmann distribution, but now it's flip-flopped, right? So energies on the y-axis, and the fraction of molecules with a particular kinetic energy are on the x-axis. And then you can imagine this is like two different plots just jammed together to show how they relate to each other. It's not like you have a continuous axis all the way along here. But what this shows is, okay, for your reaction to occur, you need to have this amount of energy from the reactant to the product. And then, all right, if you have a lower temperature, you have overall less energy available, and then only the molecules here will have the right amount of energy in order to go this height, to go from the reactant to the transition state. Then you increase the temperature, now there's all these molecules, right? A lot higher fraction of molecules that have this amount of energy, and then your reaction will occur faster. Now, if you have a reaction that occurs by multiple steps, then it looks a little different, but all the concepts are still the same. So we have our reaction coordinate diagram back. X-axis is just progress. We're going to go from reactants through the first step. And so this has an activation energy. We'll put a little subscript 1 to show it's the first step. It has a transition state on the top. Okay. And then here's the intermediates. Usually higher energy than the reactants, but I guess not defined that way. And then from the intermediate to the second bump here is the transition state of the second step, and it has its own activation energy. And then the products are on the right. Now, if you start over here, the hard part is going from the reactants to this first transition state. So this is going to be where the first step is rate limiting. Once you have the energy to surmount the first step, then it's really quick to get to this products, because if you've got the energy for the first step, you also have the energy for the second step. So this would show the first step is rate limiting. Now, this other version here shows the second step is rate limiting. So you start from reactants on the left, products on the right, again, per normal. And then your second step, the activation energy is much greater than the first step. And so when you start the reaction, getting over this first transition state will be pretty quick. But then you don't have the energy guaranteed to get over the second transition state. And so that's the one where it's going to limit the rate of your reaction. Once you get over that, you get to products. So this shows the second step is rate limiting. And this also shows why sometimes, maybe often, you have an equilibrium here between the reactants and the intermediate, because if this activation energy 1 is lower than, say, the thermal energy, then it's pretty easy to go back and forth and back and forth and back and forth, so you can have an equilibrium there, but then it's less frequent to have the energy to get up over this transition state. Whee! Okay. I'm done. Now, let's get back and look at the Arrhenius equation again and see how this depends on temperature and deal with the mathematics side of this. So you can plot this. You can plot rate constant as a function of temperature, and you'll see it increase for the reasons we talked about. Now, you can make a linear relationship out of this if you want, because say you're using Excel and you can only fit straight lines. And so if you plot the natural log of the rate constant by 1 over t, you get a plot that looks like this, and you have your activation energy. And so this is one way to experimentally determine what this activation energy is. Find your rate constant at different temperatures, and go from there. Now, this equation, the Arrhenius equation, describes this line, well, I guess the linear version describes this line. And so once you know activation energy, you can then figure out, for any given temperature, what the rate constant is. And so one thing we do in Gen Chem is we talk about, say you have 2 points, how do you convert from one to the other? And then if you know the rate constant and the temperature at 1 point, say, and then you know the activation energy, you can find then at another temperature what the rate constant is, or vice versa. And so this turns into just a plug and chug. You can figure out what the variables are pretty simply. Whenever you're talking about rate constants changing with temperature, oh, here's the rate constant in one temperature, what's the rate constant at another temperature? Or, at what temperature is the rate constant this? Then you can do that. You plug the numbers in and go. So here's an example. So we have N2O4 decomposing. We have the activation energy. We have the rate constant at 30 Celsius. And then we want to find the rate constant at 300 Celsius. Okay, here's the equation. And of course, you'll have this on your info sheet. And we want to label out what's happening here. T1 is the temperature. K1 is the rate constant at 30 Celsius. But now we have to convert this to Kelvin because we're ultimately dividing by temperature. And when you divide by temperature, then Kelvin really matters. It's when you subtract that Celsius or Kelvin doesn't matter. So say in the numerator, that wouldn't matter. But the denominator, since they're multiplied together and divided by the whole thing, you need to have it in Kelvin. All right, T2 is the 300 Celsius in Kelvin. We're trying to find K2. So let's just plug stuff in. And you're going to want to use the joules per mole Kelvin version of R because you need to cancel out joules. Also, typically, your activation energy is in kilojoules per mole, and your R is in joules per mole. And so you got to fix that somehow. Okay, so here we are. We fix that. And then you can just evaluate the whole right side. Now, let's move this up. We want to get rid of this natural log. So if you take e to the both sides, then that'll get rid of the natural log. So if we look at the right side, remember when we do anti-logs, even base e, you have sig figs that come from the number of decimal places. So 10.0, that 0.0 is the only significant figure after we do this e to the 10.09. So this comes out with only one sig fig on the right. And then the natural log goes away on the left, so that's great. And then you can just solve this for k, and here you go. So ultimately, it's just to put numbers in and solve. The pain in the bottom is if you have to solve for temperature. So if you get both rates constants and one of the temperatures, picking the other temperature out of that is an algebraic pain in the butt. Doable, but just kind of a pain. So I highly recommend, if you solve for anything, especially temperature, to then later plug all 4 numbers back into this formula, evaluate the left side in your calculator, evaluate the right side in your calculator, and make sure you get the same number. It's just an easy way to save you trouble on the test for making a silly algebra mistake. Okay, and that's all I have for now. Thanks for watching.